Welcome to BrightBoundX, where the invisible becomes visible, and the ordinary becomes extraordinary. Don't forget to like, share, and subscribe for more stories that will shift the way you see our world. Today, we're diving into a hidden world that powers nearly everything you see around you, from your phone, your laptop, your car, to the satellites orbiting Earth. You've likely never seen it before. In fact, you can't see it with the naked eye. Yet it's there at the heart of our digital civilization, the computer chip. Now, imagine zooming in on a postage stamp-sized square until it's magnified 500 times. What you see isn't just silicon, it's a metropolis, a bustling city of microscopic machines, a place where billions of electrical pulses travel at lightning speed through copper highways, weaving across stacked skyscrapers of technology. Each section of this city has a different job. Some process logic, others store memory, and all of them are constantly busy. Welcome to the Silicon City. But what makes this city come alive? Transistors. Think of a transistor as a tiny switch. It either lets electricity pass, or it doesn't on or off. That simple mechanism, when repeated billions of times, creates logic, memory, and processing power. A single modern chip can house over 50 billion of these transistors. And we're not just making one chip at a time. Globally, factories manufacture over 1 trillion chips every year, which adds up to a jaw-dropping 20 trillion transistors every second. How is that even possible? Well, we don't build these devices the way you might build a car or a house. There's no team of microscopic construction workers. Instead, we use a process that might sound like science fiction. We build using light. The method is called photolithography, and it's the reason we can construct all the intricate features of a chip simultaneously. Not brick by brick, but layer by layer, all at once, with insane precision. It begins with a humble silicon wafer, which looks like a thin, shiny disk. But this wafer is far from simple. It's the purest man-made material on Earth, with fewer imperfections than a diamond. It's thoroughly cleaned using strong chemicals and solvents to ensure there's no dust, grease, or microscopic contamination. Then it's baked in a furnace where oxygen gas creates a thin coating of silicon dioxide on its surface, a crucial insulating layer. Next comes a substance called photoresist, a light-sensitive liquid that's spun onto the wafer like syrup on a pancake. Once hardened through baking, the wafer is ready for exposure. Now comes the magic. A pattern mask is placed over the wafer. Ultraviolet UV light, precisely tuned and extremely intense, shines through this mask, selectively exposing only certain regions of the photoresist. In those areas, the light chemically weakens the material, like sunlight fading ink on a page. After exposure, the wafer is bathed in a developer solution that washes away the weakened photoresist, leaving behind a stencil of the pattern from the mask. It's as if a blueprint has been printed directly onto the surface. But we're not done yet. The next step is etching, removing the parts of the silicon dioxide layer that were exposed. Specialized gases in an etching machine attack the wafer's surface like microscopic sculptures, carving tiny valleys where the mask allowed the light to pass. What's left is a textured landscape of features just a few nanometers wide. That's the base. Now, it's time to add functionality. Using powerful machines called ion implanters, charged atoms like boron or phosphorus are fired into these etched areas at extremely high speeds. These atoms embed themselves into the silicon, changing its electrical properties. It's how we create N-type or P-type regions, the building blocks of transistor behavior. Each of these steps is repeated over and over, layer after layer, building vertically like a high-rise apartment. But here's the catch. As more layers are added, the surface becomes uneven. Imagine laying bricks without smoothing out each layer. You'd end up with a mess. To fix this, engineers use a method called chemical mechanical polishing (CMP). Think of it as ultra-precise sanding. A soft pad, soaked in a slurry of microscopic abrasive particles, gently smooths the surface until it's flat, so flat, in fact, that even atoms would have a hard time finding bumps. Once the surface is perfectly even, more layers are added: copper wires for connectivity, insulating materials, more photoresist, more etching, more ions. Hundreds of tools, each performing specific tasks, are involved. And every tool must work in perfect harmony inside a factory that is one of the most advanced environments ever created by humans. These factories are called fabs, short for fabrication plants, and they are the temples of modern technology. A single chip may require over 1,000 individual process steps, and it can take up to 3 months to turn a raw silicon wafer into fully functioning chips ready to be packaged and shipped. Each wafer, often the size of a large pizza, contains hundreds of chips. Every square millimeter of that wafer is precious. A single speck of dust can ruin a batch worth millions of dollars. That's why fabs operate in some of the cleanest environments on Earth, cleaner than surgical operating rooms. Air handlers filter and recycle the air constantly, while workers wear full-body clean suits to avoid contamination. Even the water used to clean the wafers is so pure that it would be toxic to drink. It contains 0 minerals or impurities. It's hard to overstate how extreme these environments are. Inside a fab, there's no room for error. Every chip must meet precise tolerances measured in nanometers, 1/1,000,000th of a meter. That's like trying to cut a human hair into 100 equal slices, and making each slice identical. Miss the mark, and the chip fails. But get it right, and you have a miracle of engineering, capable of powering AI, connecting billions of people, or guiding spacecraft. We've already taken a journey through the elegant complexity of chip making, the astonishing precision, the powerful machines, the atomic level control. But now, we need to talk about the other side of the silicon coin. Because as impressive as this technology is, it comes at a steep cost, one we're only beginning to understand. Let's start with water. To keep every wafer clean, every surface polished, and every tool running, fabs use a staggering amount of ultrapure water, also known as UPW. This isn't your regular tap water. It's been filtered, boiled, deionized, and stripped of every trace element. It's so clean, it becomes chemically aggressive, able to dissolve anything it touches, including your skin cells. Every single wafer can require thousands of gallons of this ultrapure water. And after it's used, that water can't just be dumped. It contains trace acids, metal residues, photoresist particles, and dangerous solvents. Before it leaves the facility, it must be treated, its pH neutralized, its toxins filtered out. But that treatment requires more chemicals, more filters, and more energy. On average, it takes about 5 gallons of waste water per wafer pass, and that number increases drastically during the CMP process, where slurries of ceramic particles are constantly flushed to prevent clumping. Without this flow, the abrasive particles could clump together and scratch or destroy the fragile copper lines embedded in the wafer. So fabs use water not just as a cleaner, but as a buffer, a lubricant, a carrier, and sometimes even as a chemical reactant. Multiply that by millions of wafers per year, and you start to understand the massive environmental footprint. And then there's energy. These facilities don't sleep. They operate 24/7, 365 days a year, because once a wafer enters the fabrication process, it cannot stop. Halting a fab mid-process risks contamination and catastrophic losses. So the furnaces stay hot, the vacuum pumps stay on, the air filters keep whirring. Even idle tools must maintain their environmental parameters. Fabs use massive amounts of electricity. According to estimates, a large chip-making plant can consume as much power as a small city. And it's not just the lights or machinery, it's the constant refrigeration to stabilize temperatures, the exhaust systems that filter toxic gases, and the massive compressors that generate ultra-clean nitrogen gas to blanket the wafer surfaces. Some of this energy is renewable, but a lot of it isn't. And while we're on the subject of gases, let's talk about greenhouse emissions. Many of the gases used in chip production, like perfluorocarbons, PFCs, sulfur hexafluoride, or nitrogen trifluoride, are among the most potent greenhouse gases known to science. Some of them have a global warming potential, GWP, thousands of times higher than carbon dioxide, and they can persist in the atmosphere for centuries. Fabs attempt to mitigate this using systems called scrubbers, which break down toxic gases into less harmful components, often by converting them into liquid waste that can be treated. But scrubbers themselves require power and maintenance, and they're not 100% effective. Which brings us to the chemical core of the process, photoresists. In modern chip making, one type of photoresist stands out: PFAS-based materials. PFA is short for per, and polyfluorocally substances are incredibly useful in manufacturing. They resist heat, repel water, and don't degrade easily under harsh conditions. That's exactly why they're used in the most advanced photolithography steps, where features are etched into silicon at sizes smaller than a virus. But those same properties make PFAS a nightmare for the environment. They're known as forever chemicals because once released, they don't break down. They accumulate in water, soil, animals, and ultimately in humans. Exposure to PFAS has been linked to various health issues, from immune system suppression to cancer. And while the amounts in a single chip might be microscopic, the cumulative effect of global chip production is cause for concern. Governments are beginning to regulate PFAS, but alternatives are limited and switching materials could slow progress in making smaller, faster chips. This is the fundamental tension at the heart of modern chipmaking. We want more power, more speed, and more intelligence from our devices, but the technology that gives us that progress is hitting environmental and physical limits. Let's take water scarcity, for example. In Taiwan, one of the world's biggest chip manufacturing hubs, recent droughts have created a shocking trade-off. Local governments have had to cut off water access to farms to ensure fabs continue operating. Think about that. Agricultural land goes dry, crops die, so that fabs can keep producing chips for smartphones, cars, and servers. It's not a one-time event, it's becoming the norm. Because fabs are so valuable economically, they're prioritized. Governments and cities bend over backwards to keep them happy. In some cases, entire regions are redesigned to meet the water and power needs of a new fab. But how long is that sustainable? At the same time, the economic pressure to build more fabs is stronger than ever. Every country wants to build its own chips to reduce dependence on foreign suppliers, especially amid geopolitical tensions. The result? A global construction boom, massive, expensive, resource-hungry factories rising across the US, Europe, India, and Southeast Asia. We're entering an era where chip-making is no longer just a technological marvel. It's a geopolitical weapon and a resource war. So what's the path forward? Fortunately, the industry isn't blind to these problems. Major companies are investing heavily in greener fab facilities designed from the ground up with energy efficiency, water recycling, and emissions reduction in mind. Some are experimenting with closed-loop systems that purify and reuse every drop of water. Others are using AI-driven controls to optimize every process in real time, minimizing waste. New materials are also being researched, photoresists that don't contain PFAS, or etching gases that are less damaging to the climate. But these transitions take time. They take investment, and they require a global commitment not just from manufacturers, but from consumers, governments, and regulators. Because in the end, every chip we use, every tap on your screen, every streamed movie, every voice command has an invisible cost. The challenge of the 21st century isn't just to make chips faster or smaller. It's to make them smarter, cleaner, and more sustainable. And maybe, just maybe, the chips of the future won't just power artificial intelligence. They'll help us build a better world. Thanks for watching BrightBoundX. If this changed the way you think about technology, hit that like button, subscribe, and share this video with someone who should know what's really behind the screen. See you in the next episode.